In this video, we're going to go over the answers for the acids and bases part B in class activity. Now, one of the things that we showed you in class was this concept map for relating pH and POH and OH concentrations in H+. So this concept map is available to you in PowerPoint form in your modules on Canvas. But it's just showing you how you can relate the pH to the POH and the pH to the H+, and all those different ways that these relate mathematically using just these equations here. In question 1, calculate the concentration of the hydronium ion in a solution that contains 5.5 times 10 to the minus 5th molar OH at 25 degrees C. And they want you to identify the solution as acidic, basic, or neutral. So the pH is the negative log of the H+. And so H+ we can use interchangeably with the hydronium ion. And we also are given the hydroxide concentration. So the POH is the negative log of the OH. So I can find the POH by taking the negative log of that OH concentration. And then because I know that pH plus the POH equals 14, I can find the pH. So then I can take that pH and find the hydronium concentration here by taking 10 raised to the negative pH. So that's my game plan here. So POH is the negative log of the OH. So I plugged in my concentration of OH here. So I get a POH of 4.2596. And then since pH plus POH equals 14, so pH equals 14 minus the POH. So 14 minus the POH, this gives me my pH. And since my pH is greater than 7, it's going to be basic. And also to get the hydronium concentration, we're going to take the pH. So we're going to go 10 raised to the negative pH. And so this is how I'm getting that hydronium concentration of 1.8 times 10 to the minus 10. So there that is for B, but that one says acidic, and we already said that it's basic. So this is how we're getting D as the correct answer for number 1. And in question 2, we're asked to calculate the pH of a solution. And this time we're given the hydronium concentration. So remember pH, anytime you see P just means take the negative log. So negative log of the H, so negative log of the H+, we're given that concentration here. So the negative log of that, if we put that in our calculator, gives us 4.62. And so that's how we're finding an answer of D. Now in 3, we're calculating the POH, and this time we're giving the hydronium concentration, so the H+ concentration. So since I'm given the H+ concentration, I can find the pH, and then pH plus POH equals 14. So this is how I'm going to find that POH. So pH is the negative log of the H+. So I plug that in. I'm getting a pH of 4.62. And so 14 minus that 4.62 gives me a POH of 9.38. This is how I'm finding the answer for number 3. Now in 4, we're calculating the hydroxide ion concentration in an aqueous solution, and they've given us the pH. So we need the OH concentration, and we're given the pH. So if pH is 9.85, we're going to do, so one of the ways I'm going to convert my pH into my POH. So 14 minus the pH can be my POH, that's 4.15. And POH is the negative log of the hydroxide concentration. And to get the POH, the hydroxide value, I'm going to get 10 raised to the negative POH. And so this is how I'm getting 7.1 times 10 to the minus 5th. This is how I'm getting C for that answer. Now in question 5, they want to know the pH of this concentration of perchloric acid. And perchloric acid is a strong acid. And we're going to use our Rice table to set this up. So our reaction that takes place, since this is a strong acid, it completely dissociates. So all of that perchloric acid dissociates into H plus in the ClO4. And our initial concentration is 0.00598. And so we're going to subtract this amount because this is our limiting reagent. And because this is a 1-to-1 mole ratio, we're adding the same amount of H plus. And since this is a 1-to-1 mole ratio, we're adding the same amount of the ClO4. So all this is used up till there's nothing left, and it creates the same amount of the hydronium concentration as well as the ClO4 because of that 1-to-1 mole ratio. So if this is the concentration of the H plus at the end, when the reaction is done and goes to completion, we can take the negative log of that to get the pH. So if we take the negative log of that value, that's where we're getting 2.223. So that's how we're getting the answer for E for number 5. Now 6, kind of similar, but this time we're given a weak acid instead of a strong acid. So anytime we've got a Ka or it's not one of those 6 acids we've asked you to memorize, it's a weak acid. So I'm setting up my rice table again. So I'm starting off with my reaction. So here's that acid breaking up into the H plus and the C6H5CO2. So that's that conjugate base that it's creating. So this is a weak acid, it partially dissociates. So we need that 2-way arrow instead of a 1-way. And so initially they tell us we have 0.461. And because this is a weak acid, we know it only partially dissociates, but we don't know by how much. So that's why we're saying we're going to lose some amount X. So minus X here, and it's a 1-to-1 mole ratio, so plus 1X here. And it's a 1-to-1 mole ratio, so it's plus X here, plus 1X here. And the ending amount, so we're going to add these two together, so 0.461 minus X, and then X for the H plus, and X for our conjugate base. And we're setting up the K expression so that products over reactants, so X times X over the 0.461 minus X. And so they told us that that Ka equals 6.5 times 10 to the minus 1, 5. So I'm plugging this in here. And so I'm going to use the approximation that X is pretty small. And so mathematically that makes that a lot easier. So now I just have to multiply both sides by the 0.461 and take the square root of the X to find X. The X, remember, is the concentration of the H plus. It's also the concentration of the conjugate base. And so I'm looking for the pH, and that's the negative log of the H plus. So I can do the negative log of X, and that's where I'm getting 2.26 as the value. And just to show you that this approximation works, look how small that X is. So when we subtract this from the 0.461, it doesn't make much of a difference here, but especially when we take into account the number of sig figs. And there's a pretty big difference between these numbers with the multiple choice. Okay, let's look at number 7. So 7, we're asked to determine the Ka of a weak acid, and they give us the concentration of the solution and the pH of the pH of the solution, which is 2.80. So we're taking this unknown acid HA, and it's dissociating. And we're setting up our rice table. And initially our concentration is 0.294. And so the initial amount of the H plus and the A minus is 0. So the change is minus X plus X plus X, because it's a 1-to-1 mole ratio. So the ending amounts we have here. And then we're going to set up our K expression. So products over reactants. So product times product over the reactant. And we're looking for the Ka, so that's what we're looking for. Now the other piece of information, remember that they gave us, is the pH, and they told us it's a 2.80. So I can use that pH to get the X concentration. So if I take the pH is 2.80, the H concentration is 10 raised to the negative 2.8. that gives me a hydronium concentration of 0.00158. And so this is our X. So I can plug this in here and here. And when I plug that in, that's how I'm getting a Ka value of 8.5 times 10 to the minus 6. So if you have questions on these, please make sure you come see me during office hours or ask me during class, but I will record the other in-class activity solutions as well.